here also, right? My z would be 0. Now, this extends backwards like this also. If I go 2 backwards, negative 2 on x, and y is 0, I'd be here. And if x is 0 and y is negative 2, I'd also be here. Do y'all see that? So here's your paraboloid. I mean, it comes down like this, goes in the back like that, comes over here like this, comes out like that. And what should it be on the ground? What should the shape be on the ground? A circle, right? And the way you know that is just let z be 0. If z is 0 here, right, you're forcing that thing down to the ground. And if I let z be 0, then that equation 4 minus x squared minus y squared must equal 0 is the same as 4 equals x squared plus y squared, which is a circle of radius 2. So this should be a circle on the ground, right? So y'all see that? I'm trying to find the volume, right, bounded by that paraboloid and the xy plane. So it's that object that I just drew there, right? So what is my region of integration? What's the floor that I'm integrating over? It's this circle, right? So I'm going to draw the region of integration over here. Right? It's that entire thing. And I could do that maybe as a type 1. It might be messy because circles aren't functions. But if I convert this to polar, I think I can handle that. What would my restrictions be? I have to find restrictions on both theta and r. 0 to 2 pi, right, would rotate me all the way around. And then my radius should go from 0 to 2. I'm curious about your reaction to this. What's that? Well, what does the red draw? Does it draw half a circle? Let's talk about the black one first. The black one, I can point out any angle between 0 and 2 pi, right? So I point out here, and I can walk out anywhere between 0 and 2. So it's everything on that line segment. I rotate a little bit, do it again. All the way around, keep going, I draw the whole circle, right? That's what this says. What does this say? I'll use a red marker. This time, I face out between 0 and what? Only pi. But I'm allowed to walk out negative 2. So if I'm standing here and I walk out to the right 2 and backwards 2, I draw the entire x-axis, right? Right here? This little segment, not the entire thing. But now what if I rotate just a little bit? I'm going to get this part and this back part. And I do that, I come up all the way up here, I get this part and the part below. So I basically have shaded out so far this part, right? Just by rotating that much. And if I rotate another 90 degrees, I'm going to get this back part also. So there's actually multiple ways you could do this problem. You could, does that make sense? Normally we don't like our radius to be negative though, right? The radius is like how far out you walk, but there's nothing restricting us from making our r negative. Now normally we don't do that, but it can be done. I mean, you can still work it out the same way. All right, we've got our region. Okay, so the next thing we would need is we need to be able to define our function of x and y converted over to polar. So what is f of xy here? It's got 4 minus x squared minus y squared, right? Now if I go to polar, that means everywhere I see x, I replace it with r cosine theta. Everywhere I see y, r sine theta. So if I'm going to switch this over, f of r cosine theta, r sine theta, it would become 4 minus r squared cosine squared theta minus r squared sine squared theta, right? That's what that would become. And what can you do with that? You can factor in r squared out of each of those, right? How about a little bit more? How about a negative r squared out of both of those? What would you be left with? Cosine squared theta plus sine squared theta, which is 1. So this is just 4 minus r squared. Now you could have noticed that beforehand had you rewritten this as 4 minus x squared plus y squared. And do you remember when I was showing you relationships between Cartesian and polar? I said one relationship we had was x squared plus y squared was r squared, right, from the Pythagorean identity. That saves you a little bit of trouble. So anytime you're doing a problem and you're converting from Cartesian to polar and you see x squareds and y squareds together, you can be thinking, can you get that to turn into a 1? Or, sorry, can you get that into r squared, I should say. All right, so you ready to set this double integral up? It's a double integral. I'm going to go ahead right now and write r dr d theta. I'm going to write that right now because I know when I go to polar, I'm always going to have r. Then dr d theta, I have choice there in the order, but I'm just going to stick with that. That means my theta is going to be the outside limits. 0, 2 pi is what we're using. And my radius is the inner integral, so the limits there were 0, 2. And then what we are integrating, 4 minus r squared. Bam. We're done. That's not worth integrating any further, right? Distributing r through 4r minus r cubed. Integrate, that should be pretty clean. Can I dot, dot, dot this one? Equals dot, dot, dot. That is significantly easier than doing it the other way, which would have been to somehow break up that circle into type 1 regions from last class Cartesian. It would have been a disaster. All right, questions, comments? Y'all look tired. Some of y'all are falling asleep. Please don't fall asleep. Go do some jumping jacks outside or something. I know y'all are like on Easter sugar overload or something, but I am too. I stayed up last night way too late watching, what was that movie with, what's his face? DiCaprio. He's out in the woods all messed up. Yeah, I don't know if I cared for that. I mean, it was okay. I was expecting a lot more. I don't know, I was expecting a lot more. I mean, it was okay.
I mean, the guy won an Oscar for it.
Yeah. It's all right. I was a little let down, though.
I don't know, maybe you're thinking he deserved it.
The real guy who went through that deserves it. Wasn't that a true story? Yeah. Okay, I'm going to leave this problem on the board, but I'd like for us to do a pretty amazing problem. I think this is a great problem. We'll see. Verify that the area of a circle radius r is pi r squared. We all know that the area of a circle is pi r squared. Those of you who've had me for Cal 2, I verified this in Cal 2, but we did trig sub to do it. We're going to do it with a double integral now. So one thing we have to remember is something that we talked about last class. If you want to find the area of some region, capital R, It's equal to the double integral over the region of what function? 1 dA. That I told you in class last time, is that if you replace the function in here with 1, then the double integral of the constant 1 function over some region R is actually equal to the area of that region. Let's use that right now. Okay, what I want to do is find the area of a circle, right? So the region, that's going to be my region. So let's draw it. An arbitrary circle, radius R. That would make a wonderful polar region, wouldn't it? In fact, in polar, my restrictions would be very nice. Theta's between 0 and 2 pi, and R's, ooh, this is R. R is between, we have trouble here. Do you see the trouble we have? I got to use a different R. So why don't we call this, I don't want to use capital R to confuse it with region. I'm just going to use R tilde, all right? R tilde, this is a constant. See, our R here is our region. We're allowed to move through different radii values. So that R that I'm allowed to move through must be between where and where? 0 and R tilde. Everyone understand R tilde is a constant? I could have called this R naught. I could have called it anything I want. I chose R tilde. All right, set up the double integral. What does it become? The area of that circle over that region R should be equal to the double integral. It's polar, so I always have to put what in polar? RD, so I'm doing 1 RD theta. What's my restriction on R? So I can put that in there and my restriction on theta. Right here. So theta goes on the outside, 0 to 2 pi, and 0 to R tilde. Now, I could dot this one, but it's worth us finishing, right? Okay, what's the antiderivative of R with respect to R? 1/2 R squared. I'm going to evaluate that from R equals 0 to R equals R tilde d theta. Replace R with R tilde, replace R with 0. What would you get? Just 1/2 R tilde squared d theta. And now integrate this with respect to theta. This is all a constant, isn't it? So the antiderivative of that is 1/2 R tilde squared times theta. Evaluated theta equals 0 to 2 pi. Replace theta with 2 pi, replace theta with 0, and you get 1/2 R tilde squared times 2 pi. So that's just 1/2 R tilde squared times 2 pi, which is just pi R tilde squared, which is basically what we were trying to show, is that the area of a circle is pi times the radius squared. All right, so some of y'all are real tired or something because, I don't know, we just proved the area of a circle is pi r squared, and y'all didn't seem too excited about that. So that's not going to get you excited. Nothing else I do today is. Sorry. We did that with relative ease, didn't we? I mean, that took us less than 5 minutes to do with polar coordinates. If you did that in Cartesian, it would involve, trig substitution, and it's doable. It probably takes about 10, 15 minutes to do the other way. All right. Now, this is a picture of a surface, some function of x and y, which we're converting to r cosine theta, r sine theta, which creates like an upper surface, another surface g that creates a lower surface. We're trying to find the volume between these over some polar rectangle. And so this, again, to just remind you what happens here, if you're trying to find the volume between two surfaces, you subtract the two surfaces, which really just breaks down to subtracting the integrals, double integrals. And we can convert to polar and do exactly the same thing. So here's a good example. Find the volume of the solid below x squared plus y squared plus z squared equals 1 and above the cone z equals root x squared plus y squared. So hopefully you recognize the first equation as the equation of a sphere radius 1. So you have this sphere radius 1, there it is. You've got this cone z equals root x squared plus y squared, which starts at the origin in three-dimensional space, creates this cone shape. We're trying to find the volume of the solid below the sphere, above the cone. So that thing right there looks like a snow cone. Right? Does that look like a little snow cone? What's its volume? So how to do this? Any ideas? Any ideas? Sure? You seem kind of... All right.
Get the whole and then subtract the one above the cone.
Do the what?
Find the volume of the sphere and then subtract the volume of the cone.
That's a good idea. Let's think about what's being proposed. If we take the volume of the entire sphere and subtract the volume of the cone, that's not quite a cone though, but you would want to subtract this to get, I think that's what you're getting. I don't. Take a look back at this picture that I just had up here. If I'm trying to find the volume of this chunk of stuff right here, does it have a top cap? Yes, it's the f function. Does it have a bottom cap? Yes? And what about the walls of this thing? That's dictated by the region on the ground, right? So as long as you can come up with some top cap and some bottom cap to the solid, and then you can define very clearly what the region is that you're integrating over, then you should be able to get the volume. So let me take you back to this picture. Do you have a top cap? It's just slow, that's it. The top cap is created from the sphere, right? The bottom of that solid is created from the cone. So you have a top and a bottom, don't you? The question is, what's the region of integration? So you have to look at almost like the shadow of that object straight down. So if I take this object and I rotate it and I look at it straight from the top, right? Then I imagine taking this edge straight down to the xy plane. That's my region of integration. Do you all see that?
Is that a circle?
And that's a circle, yes. So again, I'm going to try and draw it on here. If you translate this thing, this red curve straight down, you get some circle down here on the ground. Okay, do you all see that circle? What we're doing is we're saying, take a point here, plug it in, right? And if I go straight up and I go in between the sphere and the cone, I will be in the snow cone, won't I? Yes? And I have to pick points all from in here and take all those up to draw the whole picture. Yes? Okay, so how are you, I think we've talked about what the region is. How are you going to find it though? Is it the radius of the sphere? No, it's not, right? It's where the two hit each other. It's where the cone and the sphere hit each other. If you imagine taking that and just going straight down to the ground with it. So to start off, to get my region, I first need to find where these two intersect. How could you do that? How could you find where those two intersect? Do it what? Huh? Set them equal to each other would work, but we would have to solve them both for z and then set them equal, right? Or you can just say, hey, look, to live on the cone, z must be this, right? So just go rewrite that sphere equation and square z, right? This right here is z squared, isn't it? And then equals 1. So you get 2x squared plus 2y squared equals 1. And that means x squared plus y squared equals a half. And that's a circle of radius. It's the radius of this circle. Root 2 over 2 or 1 over root 2, right? Those are the same things. That's your radius. Questions? Regular?
That was a neat trick. You did.
What'd I do?
Oh, I mean with the plugging z.
Oh, okay.
Z squared.
Yeah, and you know, you could even go a little bit trickier than this if you wanted to. If I know I'm going to polar, which I do, I know I'm going to go to polar on this, right? Then I could just replace x squared plus y squared with what here? R squared. And square root of r squared would be r. And so I could replace this. That first equation becomes what? R squared plus r equals 1. That's a quadratic equation. R squared plus r minus 1 equals 0. And then you could do, how would you figure out what r is there? How about a quadratic formula? And you would get a quadratic formula, and one of your solutions would be this. But we didn't do that. So, all right, we good? Can we draw the region on the ground? Okay, so we could do, we know it's a circle on the ground. It has a radius of, do y'all like 1 over root 2 or root 2 over 2? Does it matter to you? Doesn't matter. Okay, I'm going to use 1 over root 2. I'm still boycotting rationalizing fractions. I've been boycotting them for a long time. All right, polar region. As a polar region, theta is going between and r is going between. Theta? 0, 2 pi. R? 0, 1 over root 2. So I'm going to set up my double integral. I want you to pay close attention here. This is the double integral I'm trying to set up. I'm trying to set up the double integral over some region R of f of xy minus g of xy dA. That's what I'm trying to do, right? It's between two surfaces, so I'm trying to find the volume between two surfaces. My upper function, f, is the sphere. And that means I need to solve that for z. So go ahead and do that now. Solve this for z. You get z equals square root 1 minus x squared minus y squared. Now, it should be plus or minus, right? But I'm only doing the plus because I'm looking at the top cap, the top half of the sphere. And then this one's already solved for z, isn't it? So this is my f function. And this right here is my g. So this becomes double integral over r of square root 1 minus x squared minus y squared minus square root of x squared plus y squared dA. That's what it would be in Cartesian. Not only would this suck in Cartesian to integrate, our limits of integration would suck too because they would involve a circular region, so that we would have to break it up into multiple pieces, and we'd have like a top half and a bottom half, and it would just be a mess, like a disaster. That's the value of going to polar. So if I go to polar, which I'm about to do, I'm always just going to remember r d theta. Okay. My function of x and y is now going to get converted to a function of r and theta. Y'all know what we're going to replace the thing in here? Right, we're going to factor a negative out of those, and it'll be just 1 minus r squared underneath the root. Minus, and this is just going to be r. Limits of integration, theta on the outside, 0 to 1 over root 2 here. I would probably distribute the r through now. Anybody have any questions on where I got that from? I'm going to dot this one, so when I distribute this r through, I get r root 1 minus r squared minus r squared dr d theta. And we should be able to integrate this pretty easily. This one right here, basic u sub. Let 1 minus r squared be u. The derivative of it's out there, kind of. This one, 1/3 r cubed. You're in business. So if you forget this, right, if you forget that r, not only would you be wrong, but the integration would change quite a bit, wouldn't it? 1 minus r squared, root 1 minus r squared, you would do that with a trig sub instead of a basic u sub. And so you'd be doing a lot of work for nothing. So dot, dot, dot. All right, we have one last type of thing we're going to look at in this section, and we're not going to get too heavy into it. I just want you to know it's there. The idea of a type 1 region in Cartesian said that we're going to stick our x's between two constants, and our y values will be stuck between two functions. So as your x changes, your y values may vary between two functions, right? That's type 1 Cartesian. If we do something similar in polar, what we're going to do is we're going to let our theta still be stuck between two constants, so between alpha and beta. So that doesn't change. But instead of saying that the radius has to be stuck between some small radius and big radius, I'm going to say that that radius is a function of theta. The inner radius is a function of theta, and the outer radius is a function of theta. And when you do that, you get a type 1. And what happened with the type 1 over here? What was the major thing that we had to be careful with? What was it? F1 of x and, no. Was it F1, G1? G1, G2, right? What was the major difference between this and like just a rectangle? That we're going to have, or limits of integration were going to be functions, which also forced our hand when it came to the order of integration. We had no choice. We could not switch the order of integration. Same thing's going to happen here. If you have something like this, your outer limit of integration is going to have to be your d theta, because that's going to be stuck between alpha and beta. Then you're going to have dr. Your radius is stuck between two functions of theta, h1 theta, h2 theta. And then this in here, it doesn't change. F of r cosine theta, r sine theta. So you see now, oh, what am I forgetting? R. R. So see, I can't switch these because these are no longer constants. I'm going to give you one example of this. And it's basically the problem that was going to be your problem 3 for your take-home, which I've changed, by the way, if you came in late. There should be a new copy of the exam on the desk. Problem 3 is changed. I like this problem. This is a really, really good problem. A sphere of radius 3, it's actually a solid. Imagine you have a solid ball, all right? And we're going to drill through the ball. And when we drill through the ball, it's going to take some of the material out, and this ball is going to have a new volume to it, right? So here it is. You can look through there, we see, right? So the idea here is that the radius of the sphere is 3. And I come in here with a drill bit that has a radius of 1. But this drill bit, I'm not going right through the center of the ball. That would be too easy to find the volume. Instead, what I'm doing is I'm drilling so that this is the x-axis, by the way, this is the y-axis. My drill bit's coming in here. In the center of the drill bit is here, and the drill bit always runs tangent to the z-axis. So here's my z-axis. My drill bit must always be touching that and going, basically it's going straight into the sphere, right? But it's offset. Do you see how it's offset? What is the volume of the remaining object? That's the question. It's a very difficult question to answer by hand, which is why I changed it. But we can set the integral up pretty easily. Any ideas on how you'd want to do this? Find the equations. You want to find the equations of the sphere and the cylinder? Or, okay, so what's the equation of the sphere? What was our radius? I think on this problem it's 3, right? On this one, I thought take home it was 4, right? Sphere radius 3. So 9. That's your sphere. All right. Cylinder, you want the equation of the cylinder? What is the equation of this cylinder? X squared plus y squared equals 1 would be